which we have done. So when you're graphing linear inequalities, you graph the line first, like for this first one. Y is less than 5, you would graph y equals 5, which is a horizontal line. The less than without the or equal to means that it's dashed, and less than means that you graph below it. For the second one, this was in slope-intercept form, so you could start at the 3, go down to and over 1. That was your line. This one is solid because of this or equal to. Greater than means you're going to shade everything above it. Typically, I find the y-intercept and shade above that. This last one was in standard form. So for this one, I would probably find my intercepts. My x-intercept is going to be 12 over 3, which is 4. That's why this is graphed right here at 4. My y-intercept is 12 over negative 2, which is negative 6, which is right here. This is a dashed line because it's just greater than. You'll notice it's greater than, but they shaded below it. That's because there was a negative in front of my y. And if I were to get this in slope-intercept form, I would have to divide by the negative, which would flip this. So it would flip it that your y values are less than this line. So you take your y and everything below it. So the difference between equations and inequalities is equations are equal and inequalities are not equal, hence the term inequality. Right? Which means that your answer for inequalities is going to be shading. It's going to be a whole set of numbers, not just one number. Where when we looked at a systems of equations, if it had an answer, it was either one number where they crossed or it was the whole line. Whereas here, it's going to be you're shading things. So systems of inequalities then give you a group of points. Where before we had the break-even point is what we were looking for. When you do systems of inequalities, you can see the set of numbers that would give you a profit or the set of numbers that would give you a loss. Because there are a combination of numbers that would do those things. And so we're going to start using it to just graph, and then we're going to use it next section to get into word problems. Let's look at solving these systems. The whole goal of solving the system is just to graph them, right? You can graph them either way. You can either graph them by slope-intercept, or you can graph them using your intercepts, your x and y intercept. If I had something like 3x plus y is less than or equal to 4, I would probably put that in slope-intercept form. Just because if I were to do my intercepts, I'm going to get a fraction for one of my intercepts. So for this first guy here, I would probably just subtract that 3x over. And my equation would look like this. Y is less than or equal to negative 3x plus 4. All right, if I did that second one, I could either do intercepts or slope intercepts. But since I did the first one, I'll do the second one as well. Subtract the x over. I have 3y is less than negative x minus 6. And then, of course, I have to divide by the 3. So I have y is less than negative 1/3 x minus 2. So I have two equations here. When I'm graphing systems of equations, I'm going to graph them individually, and then I'm just going to see where they cross. I'm going to use my same rules as what you did for bell work. If it's or equal to, I'm going to do a solid line. If it's not, I'm going to do a dashed line. I'm going to shade above or below. So if I take this first line here, I would start at positive 4. Positive 4 with a negative 3 slope is down 3 and over 1. I'll determine that this is a solid line because I have an or equal to. So I'm going to go ahead and connect those dots with a solid line. And then I have to decide where my shading is. And so if I look at this, it is less than, which means I'm going to go below this line. And so if I were to shade below this line, it would look something like this, everything on this side of the line, because that's where my y values are going down if I look at my y-axis. Then I'm going to shade the next one, or graph the next one rather. This one right here is y is less than negative 1/3 x minus 2. So I'm going to start at negative 2. And I'm going to go down 1 and over 3. And is this one going to be solid or dashed? Solid or dashed for this one? Dashed, because it's just less than. So for this guy, I am going to dash. And this is going to be also less than. So I am going to shade everything below this line. And then you can see where they cross. So when I do these, I either use two different colors or I lightly shade, because technically it doesn't include any of this up here, up at the top, and it doesn't include this. The only thing it actually includes is going to be this section right here where they crossed over. And so this is going to be my answer. Where they crossed over is my answer. The red and the blue by itself is not part of the answer. Systems of inequalities. If you look at this, we are saying that this section here consists of all of our solutions. So technically, there's an infinite number of solutions here because it just keeps going. When you have systems of equations, you can check them, right? You can take the point where they cross over and plug it in and make sure it works for both of your equations. You can actually do that for inequalities as well. This is an infinite number of solutions, but you can pick any number that's in this. So let's say I went here and said that's the number -3, 0, or 0, -3 rather, sorry. 0, -3. I can plug 0, -3 into both of my inequalities and it should make a true statement. Should make a true statement if I plug in 0, -3. So if I plug it in here, I get 0 plus -3 is less than or equal to 4. That's true. 0 plus -9 is less than -6. That's true. So if I pick any number in this set of numbers that I am saying is my solution set, then any number xy should work and make a true statement for my 2. But if I have a no solution, then you'll see that they don't work. All right, so there are going to be times, just like when you have systems of equations, where you can have a special case. This is actually one of them. So if I graph these two, and I'm just going to graph the first one with intercepts and the second one with slope intercept because it's already kind of set up that way. The first one, if I were to say my x-intercept, let's do that with actual, there we go. X-intercept for this first guy is going to be -1, 0, my y-intercept is going to be 0, +3. So -1, +3. And then if I were to graph this guy, I am going to have a dashed line. Am I going to go above or below this one? It says less than, but what am I going to do here? It's going to flip it, right? Because of that negative in front of the y. So it's going to be everything shaded above it. So it's going to be this part right here. For this next one, it's actually nicely in slope-intercept form. So I'm just going to go straight to slope-intercept, start at the -1, go up 3 over 1. This guy here is going to also be dashed. All right. And this is going to be below. So this one's going to shade over here. All right. If I had put it in slope-intercept form, so let me take this first guy here, and I'm going to put it in slope-intercept form. Subtract that 3x over. We have -y is less than -3x minus 3. Divide by y. Y is greater than +3x plus 3. What do I notice about this and this? They're parallel, right? How do I know that? My slopes are the same. So there's only really two options for parallel here. Either where they shade is going to cross or not, right? I mean, it's possible that having parallel lines with these guys doesn't necessarily mean no solution, all right? When you have systems of equations and parallel lines, you know for a fact it's no solution, right? But for this one, you actually have two options. It could be no solution, or you could have a shaded area that crosses. Had either one of these been the opposite shading, we would have had a crossover. So if this one had shaded this way, it would have crossed right here. Or if that guy had shaded this way, it would have crossed there. Or if they had both shaded the opposite direction, this little in-between part would have been an answer. So just because they're parallel for systems of inequalities doesn't automatically mean no solution. But it can be no solution. So when you see parallel lines, you do need to check and say, okay, let me double check my shading, because I could have a no solution or I could have some solution here. For systems of equations, and I'm telling you this because they're all going to be on the same test, right? If you have systems of equations with parallel lines, automatically that's going to be no solution because they never cross. But here I have a whole set of numbers. So depending on where you shade for parallel lines could mean either solution or no solution. In this case, these parallel lines ended up giving us no solution because they shaded the opposite direction of each other. If they had not done that, we would have had a solution. But this is one of your special cases here. You could have parallel lines that never cross and your shading goes opposite of each other. If you look here, there isn't any place where the two sets cross over. So there is no point on the entire coordinate plane that will make both of those work. No point will make both of those work is what this is saying. So you do have a way to check it, and you will always either have no solution or typically an infinite number of solutions. Unless there's still infinite number, but it's going to be boxed in. So it doesn't keep going infinitely in one direction, but you still have an infinite number of points in there. Let's look at this one. These are obviously parallel lines, but I want you to graph them and tell me if they have a solution or they don't. And remember, if it's just y equals a number, it is a horizontal line. Just find that number on the y and graph it. So we've graphed inequalities with absolute values. And you can have systems of absolute value equations. You graph them the same. If you'll recall, with absolute value, inside moves it left and right, outside moves it up and down. So it's really just going to be my V, and I'm going to move it. This first one is going to move left 3. Remember, inside is opposite of what you think. So I'm going to start at the 0, and I'm going to go left 3. That's where or left 2 rather. That's where my vertex is going to be. And then I'm just going to graph it. So I'm going to graph my V over here. And then I'm going to decide, is it solid or dashed? In this case, it's solid. And then how do I shade it? In this case, below. So I'm going to look at that V, and I'm going to shade below that V. And so this guy is going to shade everything down here. Is going to pretty much shade. If I look at the next one, absolute value and then a -1, which means I'm going to start at 0, and I'm just going to go down 1. And then I'm going to draw that V at the -1 position. And then I'm going to decide solid or dash. In this case, it's again solid. And this is going to cross over my other V, which is fine. You can have it with 2 absolute values. You can have it with an absolute value and a line. In this case, I'm going to shade everything above this line, or this V. So it looks like this. Everything here is shaded. And you'll notice I have a crossover section right here. That goes on infinitely that way, but that would be my answer, were those crossovers. So the same thing's true for absolute values. You can have an absolute value mixture with its 2 of them, or like I said, the example that I have you doing has a linear one. But you shade them just like we did in the last chapter. So go ahead and try this one. This is an absolute value and a line. Absolute value and a line. And absolute values can be dashed as well. They don't have to always be solid. So you'll notice on this one, you actually have 3 different lines. It says graph the system and find the vertices of the region representing the solution, okay? Vertices indicates you're going to have a closed region because you can only have a vertex if the lines cross, really. And typically vertices indicate that you have some type of polygon. And so when you graph these particular ones, and they're all set up where you can do it with your intercepts. So if I look at this first one, the intercept, x-intercept for this first one is just going to be 12. My graph's not quite big enough. My y-intercept for this one is going to be -3. So I may actually graph this one by slope-intercept so that I don't have to go that far. So we'll just say y is greater than or equal to -1/4 x minus 3. All right, the second one I can do by intercepts because I have room. My x-intercept of my first one, or my second one, is 2. My y-intercept of this guy is also 2. And then the third one, my x-intercept is -2. My y-intercept is +4. So if I graph these, I have 3 different lines. -3 is my first line, or my first y-intercept. So -3 here. My slope is -1/4, down 1 over 4, or up 1, left 4. And then my line here is going to be solid. So I'm going to do this just the same way. And I'm actually going to wait to shade this guy. You can shade as you go, but I'm going to wait at the end and shade. Here I have x and y intercept of 2. So positive 2 here, positive 2 here. This is also going to be a solid line. And it's probably going to just barely, I'm going to extend that guy out some. So I'm going to extend this line out so we can actually see the vertex. All right, we're going to do a lot of this in the next section with word problems. And then this guy, y-intercept of 4, x-intercept of -2, he is also going to be a solid line. So we're going to do a solid line here. And you can see that I've created a triangle. All right, and so I need to figure out where I'm shading. Just because you have a figure like this doesn't mean it's going to be shaded on the inside. For your word problems, it typically is, but sometimes it's not. So you really want to pay attention to where your shading is. For this first one, my shading was above it, so it is up here. For my second one, it's below it, so we're still in this region. And for the third one, it says greater than, but it would flip to less than, so it's actually going to be here. So they are all going to cross within this region. And so you end up having a closed region. Now, it's still technically an infinite number of solutions because you have all those numbers in between that are not integers. But you have this closed region that is a triangle here, all right? And so when you have a triangle like this, and mine's probably a little bit off because if I were to go down, it probably crosses somewhere closer to here. They often ask you for where they cross, where the vertices are. And here's the thing. This is going to be a hard one to estimate, right? If you look in your book, where does this one actually cross? Well, it says -2/3 and 8/3. No one's going to probably guess that perfectly, -2/3 and 8/3, right? All right, and so when we start doing these where it asks for the vertex, where they cross, you literally have to solve for where these two lines cross, which means you have to use one of your methods other than graphing to figure it out, because graphing didn't tell me enough, right? Graphing told me the region, I can see the region, but if it wants the vertex where they cross, my graph wasn't good enough. If you look at this one, they crossed at -4, -4. Well, clearly I did something wrong in my sketching of my graph, right? Does that make sense? And so you want to use your method. Maybe use elimination here. Make these equal. So when we start solving these in the next section, and it says, where is the vertex for these two lines? You want to set it as a line, and you want to solve it just like you would solve by your methods before, either by substitution or elimination. Does that make sense? Because you're going to have to actually figure out what these exact points are where they cross, because that's going to be how you solve your word problems. You need to know the vertex. And in order to find the vertex, you have to know exactly where it crosses. The only way to figure out exactly where these cross, especially if it's something like in the thirds, is to actually set them to equalities and use your method of either substitution or elimination. Because if you look ahead, you're going to find that these points tell you either the maximum or the minimum of some of these questions. And so while the graphing piece is easy, all the ones we've done this far are fairly simple, you're going to have to then apply the method of solving equations to this as well to solve exactly where your vertex is. And so in this case, my vertex was at -2/3, 8/3. That's one of them. Over here, it ended up being at -4, -4. And over here, it ended up being at 4 somewhere, -2, I think is what they said. So mine were like, I don't know what I did, but mine are crazy, all right? Especially if you use intercepts. Intercepts you can't walk down. And so when I use the intercepts here, sometimes it makes it a little bit more difficult. But sometimes in a word problem, intercepts are really the only way to do it. It's because you're going to have these huge graphs that are in the hundreds. And so you're going to have to be estimating. All right, so let's do one where you just graph the 3. I just want you to graph these 3. I'm not going to make you do the where they cross each other right now. I just want you to graph the 3 inequalities for me and get your region.